So let's determine the isoelectric point of the amino acid aspartic acid, aspartate. And of course the isoelectric point, abbreviated as Pi, is when the charge equals 0 on the molecule. So how do we calculate that? Well, we are going to titrate the aspartic acid solution with hydroxide ion in order to remove the proton that is bound to the molecule. So let's look at our scale of pH. We'll take this up to 12. Now at very low pHs, under acidic conditions, we are going to see the aspartic acid is going to be fully protonated. So all three functional groups will be protonated under these conditions. So the charge on this particular structure, the carboxylic acids are neutral. The primary amine has a +1 charge. So the overall charge is +1. Now as we titrate the hydroxide into the solution, the pH of course will increase, becoming more basic. We will come to our first inflection point on the curve, and this first inflection point will be at a pH of 2.1. Now this point here is a buffering region, and buffering means that the functional group is half protonated, half deprotonated. So this here represents pKa1. So what functional group is this pKa1 representing? If we draw the structure at this pH of aspartic acid, we will see that the functional group, the carboxylic acid on the alpha carbon of the amino acid, is now deprotonated. And here we're talking about a 50% deprotonation. So 50% of the molecules in solution will have a negative charge and 50% will be neutral. So this functional group overall will have a 0.5 negative charge. The R-chain carboxylic acid is still protonated, so that will be neutral. The primary amine, because this is a basic group, will still have its +1 charge. So the overall charge on this particular molecule is +1 minus 0.5, so the overall charge is +0.5. Now once we increase our titration, continue our titration of the hydroxide ion, we will be leaving the buffering capacity of this particular functional group, and that means that the pH will start to climb again until we get to the next buffering zone of a functional group. This is termed pKa2. And for aspartic acid, the second pKa is at pH 3.9. Now at this particular pH, let's see what the structure of aspartic acid will look like. So at the second pKa, we can pretty much assume that the carboxylic acid that's attached to the alpha carbon is now almost fully deprotonated. So this is going to contribute a charge of -1. The R chain, carboxylic acid, is now the pKa2, and so this is 50% deprotonated, which means of all the molecules in solution, 50% will be deprotonated and contribute a -0.5 charge. Now, because we are still under very acidic conditions, the primary amine here attached to the alpha carbon will remain protonated and contribute a +1 charge. So to calculate the overall charge on this particular molecule at pKa2, we just add up the contributions of charges of each functional group. +1 plus -1, 0, -0.5. So the overall charge on this molecule at pKa2 at pH of 3.9 is a -0.5. Now, as we continue our titration of hydroxide ion, we will leave the buffering zone of the R-chain carboxylic acid, and the pH will begin to climb. Finally, we will reach a plateau that is our final buffering functional group, and this is pKa3 of the aspartate molecule. This pKa is represented at pH of 9.8. So, of course, being so basic, this is going to be representing the pKa of the primary amine. So what does this molecule look like? At pKa3, pH of 9.8, now we are beginning to titrate off the proton on the primary amine. So this pKa represents the pH at which this primary amine is half deprotonated, which means that this will contribute a positive 0.5 charge, because half of the amine will be protonated, half will be deprotonated. The carboxylic acids, of course, both on the alpha chain and the R chain, will be fully deprotonated, contributing charges of -1 each. So the overall charge on this particular molecule will be -1 plus -1 minus 2 plus 0.5. So we're looking at a overall charge of -1.5. Now our objective is to identify the isoelectric point where the net charge on the molecule is 0. If we look at these two pKa's of pKa1 and pKa2, we can see that we have a positive 0.5 charge at pKa1, a negative 0.5 charge at pKa2. So based on this information, the charge of 0 will be somewhere between these two values. So the way to calculate it is the charge equals 0 equals pKa1 plus pKa2 and halfway between those two, divided by 2. And this will equal the Pi, which is equal to the pH where charge equals 0. And so if we calculate this pKa, which is 2.1 plus 3.9 divided by 2, we have a Pi equal to 3.0 for aspartic acid.